weird looking. Okay. So chapter 2, our overall idea that we're looking at is communicating data visually. And that's a big deal. We take in a lot of information visually, and another way of saying that, we're talking about graphs. And so that might not be the most exciting thing you've ever spent time talking about, is different types of graphs. Okay, but that's where we're at today. Okay. Hopefully it won't take us too long today to get through the chapter 2 stuff, because a lot of the stuff you've seen for forever, like pie charts, I mean, goodness, you've seen pie charts probably your whole life. So a lot of it's pretty familiar in this section. Okay. But even if you've seen graphs, you might not have stopped and thought about how often you see graphs. I mean, you can't walk down the hallway here without some type of little poster with a graph on it trying to convey some piece of information to you, dealing with some type of data. Okay? Especially right now, you got all the mask signs and stuff like that extra out there. That's beyond just the normal stuff that's out there. So see all kinds of graphs and things like that. Okay? All right, so in 2.1, we're starting with something called frequency distributions, okay? And then we'll get to the graph version of a frequency distribution, okay, in the next section. Oh, I remember the other thing I was going to say about graphs. I got lost and just went on. It wouldn't come back to me. But communicating information with graphs, it might not seem like it, but especially in terms of math type stuff, that's a pretty new thing, especially how popular they are. Graphs and communicating with pictures like that, the modern version of it really hasn't been around as long as you may think it has. Okay, so have any nursing majors? Yep. All right. So probably not. You might be interested to know that the first person that gets credited with really doing a statistical graph was Florence Nightingale, who started a lot of the nursing trends back in the day. So, okay. All right. So, a little bit of vocabulary that happens when we go to a new chapter. So, the vocabulary will slow down, okay, especially after we get through this first set of material for the first test. We'll still have some, but it won't be nearly as much, okay, because we'll have all the basic terms down again. Okay, so this first vocabulary term we have here is just it's a fancy term for something you already know about. Okay. It's called an ordered array. So the only reason why I even left that one in there is just so you know what it is if you see that term again, because our book does use it pretty often. All that means is you have a list of data that's in order. Okay? So you can do smallest to largest or largest to smallest, doesn't matter. Okay, but the technical name for that is an ordered array. So if you see that, don't let it trip you up. That just means the data is in order. Okay? Well, this next term we do kind of want to get familiar with here, and that's what we call a distribution. Okay. And when we talk about a distribution, we're trying to describe the structure of some data set or some population. And that's a little vague right now, but that's kind of what we're working on here at the beginning of the class, is ways we can describe the structure of different data sets. That's what we call a distribution. And we'll kind of fill that out more as we go here. Okay. That's really just vocabulary for the chapter. I need to get us ready for the chapter. And then more focused for this particular section. And we've got some more. I'm sorry. I tried to spread them out so it wasn't so cluttered as it was last time. Okay, so in this section, the thing that we're focusing on is called a frequency distribution. And all that really is, it's a table of values. Sometimes we'll have a table of individual values, and sometimes we'll have like groups of values, so like a range of values. So we'll have like data between 5 and 10, so it'll say like 5 to 10, and then 11 to 16 or something like that would be the next one. So we've got the different data values listed out in the table, and then all we do is we're just counting how often each data value occurs in our data set, and then we just write that number down. So we'll say there are like 10 data values that are between a value of 10 and 15. Okay. That's all we're looking at, but we've got the terminology that goes along with that. If we've got a row in our table for every possible data value, that's what's called an ungrouped frequency distribution. Those are less common. Most of the time what you're going to see is a grouped frequency distribution, and that's when you, instead of having one row in our table for every data value, we kind of group them together. And we have those different ranges of values. And then the number we get when we count how many times a particular data value or a data value in a range of values occurs in our data set, that's what we call the frequency. So it sounds fancy, but it's just how many data values are in that range of values. That's what we call our frequency. And then one more down here, kind of toward the bottom. Sorry for people in the back. I didn't think about that. I'll get it, try and get it better next time. Okay. Last term we have down here is called a class. And all that is one of those ranges of values. So it's, you can think about it like a category, like again, like I'm saying, the data values between 10 and 15. They have a value of between 10 and 15. And that would be a class. These will make more sense here in just a minute when we look at the frequency distribution. Three more terms. We'll be, I think we're almost done with vocabulary after these three. Okay. There's three more terms. So if we have one of those ranges of values, so maybe let me go back to like age of students in the classroom. Let's get a more concrete example there. Okay, so our data set's going to be the age of every person in here. And then if we're making a frequency distribution, maybe we're going to say we're going to have a range of people between 18 and 20 and count how many of those we have in here. That would be a class. And if we think about the range of values there, how wide is that class? How many data values could fall in there? We're going 18 to 20, so that's our class width, would be how wide that is. Okay. And on that one, it's really 3, because you would have 18-year-olds, 19-year-olds, and 20-year-olds in there, but we'll see that in just a second. Okay. And then we have the lower class limit and the upper class limit. Okay. And they're easy. And the lower class limit is just the smallest data value that can go in a particular class. So 18 to 20-year-olds, 18 would be the lower class limit, 20 would be the upper class limit. That's the largest number, the largest data value that can go in a class. So those are not too hard to grasp. Okay. Questions on any of the vocabulary before we actually look at one of these? If it sounds complicated, it's not, I promise. Okay, so let's look at some data and then see how that data could be turned into a frequency distribution. Okay, so here's a table with some data in it, and it's in order from smallest to largest. So that's what we call an ordered array. And we want to look at how this turns into a frequency distribution. We're not going to worry about like going through the whole process of starting with the raw data and then going through all the little steps and making a frequency distribution. I just want you to understand what's going on when you see the frequency distribution. That's my big goal for us there. So here's our data. We've got the highest early career salaries with a bachelor's degree. And then we take this thing and turn it into a frequency distribution. One way it could look would be like this. Okay? So what's been done here is that we've taken and instead of having a row for every possible salary, they've put them into groups. So this is a grouped frequency distribution. And so like for our first group, our first class, okay, we're going to count all the starting salaries in our data that are between $50,000 and $54,999. Okay. And when we count how many of those we have in our data, that's our frequency. That's all that's going on. So if we look back at our data, we should be able to find 3 data values that fall in this range. Okay, so let's look real quick and make sure that's in there. So my short-term memory is terrible. I already forgot. So less than $54,999. So there's one. There's one. And there's one. And that made it easy on us because I've got them in order. I forgot that. Got 3 data values that fall in that range, so our frequency is 3. You got the idea of where these numbers are coming from? You just count how many there are in those ranges. I know that sounds, until that clicks, it can be confusing. Once it clicks, you're like, oh, that was really easy. So, okay. That's frequency. And then just to point out our other vocabulary here. So in the homework, you'll see like, what's the lower limit of the third class? That would be like a question. So this would be the first class, second class, third class. And then for the lower limit, that's the smaller value. So the lower limit would be 60,000 here. It said, what's the upper limit of the fifth class? And then 1, 2, 3, 4, 5. And the upper limit's the big number, so 74,999. Okay. Nothing bad there. All right. And one thing to take note of here, if we add the frequencies all together, so like 3 plus 6 plus 4 plus 10 plus 1 plus 1, what's that number going to tell us? Yeah. If we add all the frequencies together, that's going to be the how many data values we had in our data set. Data values in our data set. So usually when we have one of these, we don't also have the data like this. Usually all we have is the frequency distribution. So one way you can figure out how many data values there were in the data set is you add up the frequency. Questions on any of that? I wish I was somewhere in there. Okay. So a couple more little things here. And they are little things. Okay. So we've got the idea of upper limit and lower limit for a class. That's the smallest or largest and smallest values that can be in one of these classes. Something that's kind of similar, but you'll see it used sometimes, is called the class boundary. And the class boundary is just the value that's in between the upper limit of one class and the lower limit of the next class. Okay. Depending on what type of data you're working with, usually you end up with a decimal value that's in between two numbers. So like if we look back at our table here, I'm saying the class boundary would be the number between 54,999 and 55,000. So you would get 54,999.5. That would be the number that's in between those. You just add them together and divide by 2. That's the class boundary, and you can call them lower boundary and upper boundary if you want to, but we're not going to be too worried about that. Okay. And then one other term that's good to know is frequency distributions. We did that, so they're just finding the boundaries on each one of these. One other term that's useful to know, okay, is the class midpoint, and it's what it sounds like. It's the value that would fall right in the middle of a class. And to find it, it's easy. You just add the smallest value that can go in a class plus the largest value that can go in the class, and again, you divide by 2, find the middle. It's the midpoint. Okay. So the main reason for talking about these is if you see a frequency distribution, sometimes it's labeled with the boundaries, or sometimes they're labeled with the midpoint, and it's nice to know what those mean. Okay. So for like the midpoint on these, you would take 50,000 plus 54,999 divided by 2, end up with $52,499.50 or 0.5. That's just the value that falls right in the middle. Okay. All right. No, that's boring. Okay, but you run into these things a lot. Okay, so we had to spend a little bit of time on them. The main reason for us working in this section, though, is because the next 2 things we got in this section are 2 concepts that are really helpful. They're helpful for thinking about a lot of things later on in the semester. And so it's a good time to get our brain kind of started thinking this way, a couple things. Okay, so the first of these 2 ideas is called relative frequency. So frequency is just how many data values fall into a particular class. But relative frequencies, we're thinking a little bit differently. We're not just thinking about the count of how many data values we have. We're thinking about like the ratio or the percentage of our data that falls into a particular category compared to the whole data set. Calculating that's easy. It's more of the concept that's you want to think about here. So relative frequency, and we got it's like our first formula slide for the class. Okay, frequency's F. And it tells us is our sample size, or just how many values we had in our data set. So to get the relative frequency, we just take how many data values we have in that class and divide by the total number of data values in the data set. That's it. This thing, we'll talk more about this later. This thing just means addition. So this is just saying if you need to know how many data values you have in your data set, add up all the frequencies. We've already talked about that. So add up all the frequencies. So how could we take that frequency distribution we've been looking at with these salaries and change it to relative frequency? Well, we would, if we didn't have the data, we could add up all the frequencies. Figure out we've got 25 total data values in that data set. Or since we had the data, we could go back and count them. Either way, in this case. And then once we have that, we just take the regular frequency for each class. And then we're going to divide that by how many data values we had. So we had a total of 25. 3 of them fell in this class. So 3 divided by 25, or 3 over 25, that's fine. That should be 0.12. It's missing a decimal there. Okay, or, don't bother me, 0.12. Okay. Or we could change that to a percentage and say 12%. 0 is easy, 0, 0%. Here, 6 divided by the 25, we get 24%. So the idea here, instead of just looking at the counts, we can look, and it's easier to think about these percentages sometimes. Okay, so like here, it's one thing to say we had 3 data values in this class, but it can be more meaningful to say 12% of our data fell in that class. It's just a little more descriptive. Any questions on getting from here to here? Nothing? Don't be shy if you do have a question, okay? Nothing wrong if you need to ask a question, okay? All right, so that's relative frequency. Okay. And then we've got one more special type of frequency, our other big idea, and that's called cumulative frequency. So sometimes it's helpful to think about our data in these terms. So the idea here is we're accumulating frequency as we go down our table. Okay? So the cumulative frequency is always going to get bigger as you go down, or stay the same, or get bigger as you go down the table. Okay? So what's happening is, like if we're looking at the second row, the cumulative frequency for our second row would be the regular frequency for the second row plus the regular frequency of the first row. Okay? So just as we go down, we're adding the frequencies up. Okay? All we're doing there. Okay? So maybe that makes more sense if we look at it. So look at this one. So what I'm saying is that the first class is boring with cumulative frequency because it's just the same thing as regular frequency, because there's nothing that comes before it. And on this one, the second one's kind of boring because it's 0, but what we're doing is we're taking this frequency plus this frequency, and that's our cumulative frequency. The third one, we would take this frequency plus this, and that's our cumulative frequency. For the fourth one, we take the fourth plus the third plus the second plus the first, get our cumulative frequency. I'm going to do that for each one. Okay? So just to figure out the cumulative frequency for a class, you take its frequency plus the frequency for all the ones that came before. And then the last row is going to be special too, because if you add up all the frequencies, what do you get? You remember? It's 25. What's that 25 tell us? How many data values we had. Yeah, so for the total data value. So you can always think about that too. So the last row when we're dealing with cumulative frequency is always going to be the same as our sample size, or how many data values we have. Okay. Questions there? That's that section. That's 2.1. Okay, we're done with it. I know it's kind of boring. Be honest, 2.2 is kind of boring too, but we're going to get through it. Okay, and then we'll be on the more interesting stuff after that. Okay, on the more interesting stuff there. So there's 2.1 out of the way. Just some little things with frequency distributions. Okay. This thing will ever save. Yeah, there'll be some, yeah, especially on this first test because we have so much. But it'll be problems like out of Hawks though. You'll already be exposed to them. So like in the 1.2 assignment, it gives you a data set, type of data, and it says, is this quantitative or qualitative? So that's vocabulary. But I'm not gonna make you define anything. Is that what you meant? Yeah. Yeah, you're not gonna have to do definitions, okay, these terms. So as long as you have the idea, you don't necessarily have to be able to put them in any exact wording or anything like that. Okay. Okay. Any other questions you can think of? Okay. All right, 2.2, graphical displays of data, so graphs, that's what we say. So here we're just gonna run through these pretty much as quick as we can. Okay? I'm gonna mention some little things about some of the graphs you're less familiar with, but a lot of these, at least, I don't want to say most, a lot of these you're familiar with, and you've been having to look at these on SATs and ACTs and everything for forever, so they're not bad. They're not bad. So, one thing to mention at the beginning, and it's something you might not think about, but you can make a graph that's a bad graph, and you can make a graph that's a good graph. Okay, so what am I thinking about when I say we have a good graph? It needs these 4 things. Okay. So we have a good graph. It needs to have a title, so you know what you're looking at. Okay. We need labels, again, so you know what you're looking at. You want X and Y axis if you've got both. Not all graphs have both. A pie chart doesn't have it, but if you have axes, you want labels on those. If it's not your graph, you need a little citation there. I mean, you might not think about it, but that is plagiarism if it's not your graph and you're using it. And then that should not say data. That should say, thought I fixed it. Date. Okay. Not data, date. The whole purpose of a graph so we don't have to look at the data. So we don't have to have the data there. We want a date. Especially now that everything is going electronic, or is electronic, and just about. You can, pull up a graph from some website on the internet, and if it doesn't have a date on it, who knows if it's still relevant. Okay, so that is a good habit to have there too. Okay? So just some quick things there. So boring vocabulary you already know here. We got a graph. You probably do not have to write this one down. Okay. If we have a graph, what does that mean? It's just a picture that gives us an idea of what's going on with the data set. Okay. And there are all different kinds. Okay. Like I mentioned earlier, really using these things is, at least if you think about world history, it's pretty recent. Okay. So we're still developing new ways we can display data effectively all the time. Okay. The graph, and then a legend, you know what that is too. It tells you how to read the graph, and it gives you an idea of how we can identify the different categories that are displayed on our graphs. Let's see. Okay. Not all graphs have to have a legend, but if you think it's could be, reasonably possible for somebody to misinterpret what your graph's saying, then the legend's a good idea. Okay. All right, so let's look at our first graph. We start with just about the most basic, and that's a pie chart. Okay. Probably the one interesting thing I can tell you about a pie chart that you haven't thought about before is that we're specific about what kind of data works with a pie chart. And that's that pie charts deal with qualitative data. It's not useful to use a pie chart for quantitative data. Okay. And I don't know that I've ever met anybody that doesn't know how a pie chart works. I may have. I just didn't know, but it's just the bigger the slice, right? The bigger portion of the data goes in that category. But we've got some new terminology with that idea now. So the bigger slice of the pie represents a larger relative frequency. Okay. Here's a little table with some data. Okay. We've got different housing types, and then the numbers of students out of this class that live in different types of housing. And then we're going to look at a pie chart. Okay. So there, if we were having to do this thing by hand, everybody uses a computer now, pretty much. But if we're having to do these things by hand, what we would have to do is we would have to figure out the relative frequency for each one of these categories. Okay, so we would figure out how many we had in an apartment divided by the total number of data values, get that as a percentage. Okay. And then to calculate how big the pie slice should be, 50% is easy, you know it's half the pie, but for the weird ones like 12.5%, what you would do, and you're not going to have to do this, okay, but what you would do is you would take the percentage and multiply it by the 360 degrees that are in the circle. Figure out how many degrees wide your slice should be. But okay. We take that table, turn it into a pie chart. That's what we get. Okay. And I'm sorry, our textbook made this thing awful, and because it got tiny little writing on there. And I couldn't fix it for them because it's like built into the picture. It's not like typed on there. Okay. But the idea is that if you've got something like this, if you've got the letters and the writing big enough for you to be able to read it, then you should be able to look at this and in about maybe less than 2 seconds, what should stand out to you about this pie chart if you're wanting to know about what types of housing students live in. Yeah, most are in apartments. That's the idea. That's the purpose of graphical displays of information, is we want it to be fast. Because if we're trying to communicate something to people with a picture, we don't want them to have to stop and read a whole bunch of stuff. Okay? We want it to be as close to instantaneous knowledge uptake as we can get it to be. Okay? And on this one, it would be if you could read everything okay. You would look at it and say, oh wow, a lot of people live in an apartment, and then you would know. Okay? That's the idea there. Okay? No, it's not real exciting. Okay? Look, go to the next type. Okay? You've seen these two. Okay? That's a bar graph. Okay? The bar graph is the same idea as a pie chart. Just instead of putting everything in slices of a pie, we just have bars beside each other. And the height of the bar represents the amount of data, the percentage of the data that was in that category. Okay. So we use these things in similar situations. This is the same data. We're just going to turn it into a bar graph. Okay. So there it is as a bar graph. Okay. We use these graphs in similar situations. Okay, like if you look at that, and if you can read it because the writing's big enough, then it's pretty easy to see that, you know, by far apartment's the most common type of housing in this class. Bar charts do have their advantages over pie charts, though. Here we've only got 4 different types of housing. But if we had a bunch of different categories, pie chart starts getting not that easy to read. Okay? And the idea is we want the information to be as easy to get as it can be. Okay? A bar chart's a little better in those cases. It's just easier for your eye to pick up things with the bars than with a little skinny slice in a pie chart. And if you've never thought about it before, the next pie chart you see out in the world, look at it. It's probably crappy, okay? Because you've probably got one big slice. Okay, that's good. But then they've probably got like 10 little bitty thin slices that you can't even see how wide they are. That's useless. Okay? So, I don't know. We kind of need to move away from pie charts a little bit. They're a little bit too common. Okay? We use them when something else would be better a lot of times. Okay, there's a bar graph. Okay. You may have seen these next 2 versions of a bar graph we're going to look at. Just especially this first one, I think you've seen. Maybe not the second one as often. Okay, but they're still just bar graphs. But the idea here is that we're comparing two different groups. So maybe instead of just looking at the students in one class and what types of housing they live in, maybe we want to break that down. We want to take some freshman students and see what their housing breakdown looks like, and then take some senior students and see what their housing breakdown looks like. Okay? So we could do that with either one of these, side by side or stacked bar graph. So the way it works, and we got some data here. Lots of times we'll give separate colors, and that's helpful. It's a good idea if you can do it in your software, and we're moving toward it. Okay, but it's a good idea to also put like some type of pattern on the bars too. Okay? Because what if somebody can't tell the difference between red and blue? And that's not helpful. Okay? They have no idea which one's going on. If both of these look gray to somebody, they're just two gray bars beside each other and they don't know what's going on. So a little pattern can be helpful too. But so the idea here, we can look really quick and say, okay, freshmen are red, sophomores are blue. I said seniors, but sophomores are blue. And things that stand out on this, like, well, we got a lot more freshmen that live in the dorm than sophomores, right? What it looks like to me. Things like that are easy to see there. Okay. And then the other version, the stacked bar graph, instead of putting the bars beside each other, this one you don't see quite as much. But you put the bars on top of each other. So then you can kind of still compare like red to blue. Like you can see more red here, less blue. But the advantage of using the stacked bar graph is like on this graph, it's easier to see that there's more total students in dorms than apartments than on the last one. Because if you look at the last one, if I asked you, are there more total people in a dorm than in an apartment? You can figure it out, but you have to stop and do a little bit of math to be real sure. Okay? And if you're trying to communicate to the general public, they don't like doing math. Okay? It's easier just to something like that. Okay. All right. See what's next. Okay, so our tie back to last section. Okay. We had frequency distributions. If you take a frequency distribution and turn it into a graph, you get what's called a histogram. And that's really what we want. We're not so concerned about frequency distributions as we are about thinking about these histograms. And I always have, as I guess it's, I don't know, I have a pet peeve here with how our textbook describes or defines a histogram. It uses bars, but it's not a bar graph. So I'll show you why in a minute. Okay. It's really not that big a deal. It just bothers me. Okay, so you can ignore that if you want to. But what we're doing is we're taking the frequency from a frequency distribution and we're using that to give us the height of the bars and get a histogram. Okay. So get frequency histogram there. And if you figure out the different kinds of frequency, right, if we do relative frequency instead, we can make a graph out of that. And then, oh, didn't have this one. If you do, you can also do cumulative. If you take and use cumulative frequency to give you the height of the bars, you get a cumulative frequency distribution also. So if we take our data we were using, and with these salaries, we already had the frequencies on there. And if we let the different frequencies give us the height of our bars, what we're going to do is our bars, we're going to have an x-axis that runs the range of all of our data. So our x-axis will need to go from at least 50,000 or lower, and all the way up to 84,999. And then we just put a line where each category starts, and then we get our bars there. So you'll see. You've seen these before too. Okay, so we're saying between these two values, we had 3 data values in our data set. And so we've got a bar for each class. Remember, on that second class, we had 0. We don't have a bar there. They're pretty nice though, because you can, instead of having to read through that table, it's pretty easy to see, you know, what the most common range was, somewhere in between these two numbers. And this one's labeled with those 50-cent numbers that are in between the upper limit and the lower limit, those class boundaries. That's pretty common to see. You'd also take the same idea, but we use on the y-axis, we label it with our relative frequency instead. Okay. So over here, instead of how many data values we have in each category, we've got what percent of our data was in each category. And that doesn't really change the graph, right? If you look at it, it's basically the same graph as the other one. As far as the picture, it changes the scale a little bit. Like if you put them right on top of each other, it might be a little squished one way or the other. But as far as the overall picture you get, it's the same thing. Okay. There's that, and then I guess we don't have a cumulative one. Okay, so here's my thing, my nitpicky reason I don't like saying these are bar graphs. You may notice anything different about just the picture. You don't have to worry about the labels or anything. Just the picture between this, a histogram, and a bar graph. Now, on a bar graph, the bars don't touch. They don't have to touch. Okay, and you can put the bars in wherever you want them. Okay, here, this x-axis, these bars touch because the range of values go right up to each other. Right? There's nothing in between these. Little nitpicky thing. Okay. All right, probably the first type of graph you haven't seen before. Yeah, you may have seen it, but much less common. Okay. For people to have seen these when you get here, called a stem and leaf plot. Okay. And you don't necessarily have to write these definitions down. Okay, we're just, as long as you can read a stem and leaf plot, you'll be in good shape. Okay, I'll save you some writing there. The idea is we're going to have one set of numbers that we call the stems, and then one set of numbers that we call the leaves. Okay. What we're doing is we're splitting the data values, the numbers, up into different groups of digits. Okay. You'll see in a second, it'll make more sense. And then it's rare to see just a plain stem and leaf plot. Almost always when you see one, it's going to be an ordered stem and leaf plot. So what that means is that the leaves are in order from smallest to biggest. We'll see that. Okay, so let's look at one. Let's get some data. Okay. We got a set of ACT scores. And then we're going to look at how this could look as a stem and leaf plot. So if we take this data and turn it into a stem and leaf plot, anybody see your ACT score in there? I don't see mine in there. Yeah. Nope. Well, I got one of my lower ones is in there, but my highest one's not in there. All right, so then we get a stem and leaf plot. Okay. This one's not an ordered stem and leaf plot because the leaves are not in order. Right? This row is. Right? It goes 1, 2, and then 5, but this one's not because it goes 8, and then 9, then back down to 8. All right, so if it was an ordered stem and leaf plot, this first row would be 7, 8, 8, 8, 9. Right, that would be in smallest to biggest. Okay. And if we look at the key down here, okay, it tells us that a stem of 1 and a leaf of 8 represents an ACT score of 18. So here we can read off the ACT scores that were in our data. We know there was an 18, a 19, 18, 18, 17, 23, a 24, a 27, 26. See where the first digit's the stem, and then the other digits, the ones digit are the leaves. What's going on there? So what was the highest ACT score in that data? 35, yeah. So the biggest stem was 3, biggest leaf was 5, so 35. And the lowest was 18 in there. Okay. Questions on reading that? We're going to look at another one to practice a little bit. Okay. Oh, and one other thing that can happen on these, sometimes we want a graph where we compare two groups. So maybe we had like some sample data from Alabama and some sample data from Georgia, and we wanted to compare those two with their graph. What happens sometimes is they'll put the stem down the middle like it is, and then we'll have another set of leaves over on this side. And for this side, you kind of have to read it backward. You read it from the stem to the leaf instead of going this way. And then it does look more like a leaf because the stem runs down the middle and then the leaf's on the outside. So that's kind of where it gets the name. And let's look at another one. We got starting salaries for entry-level accountants. Okay. That might have been what I should have majored in. Starting salaries for entry-level accountants, and then if we turn that into a stem and leaf plot, it could look something like this. There's no like hard and fast rule about what you use for the stem and what you use for the leaves. It depends on what you're trying to show. But here our key says the stems are the tens of thousands, or the thousands really. So a stem of 40 and a leaf of 7 would give us $40,700. The reason why that worked good on this one is because we didn't have any tens or ones on the dollars, so they all ended in 0, 0. So they could do that, and it makes it look pretty nice. Okay. So what's this mean? There's nothing here. Yeah, nobody was in the $41,000 range. Right? Okay. What was the biggest starting salary in our data set? Can you see it? $51,500. Okay. How many people had a starting salary in the $44,000 range? 3. So we got 3 leaves here. I know it's kind of small for the ones of you in the back. Okay. That's it. You just need to be able to answer questions like that off of stem and leaf plot. Oh, and this one is ordered, by the way, because the leaves are in order. So that's usually how you'll see them. Okay, just a couple more. We're almost through probably the most boring section in the book, okay, in my opinion. So almost there. Okay, just to mention a few more types of grass. Okay, the first other mention is a dot plot. All it is a number line. Okay. And then wherever you have a data value in your data set, you just put a dot over the number where it would be on the number line. And if you have like 2 data values at a certain number, you would just have 2 dots and stacked on top of each other. So not a lot to talk about there. It can be pretty useful though. A heat map, they're getting more and more popular. Okay. So we didn't have these in the old version of the textbook. Okay. They've added them in the new version, but you'll see these pretty often. Okay, now, if you look around, they're trending. Okay, so you have usually use different shades of a color, and the darker color represents a bigger value, and the lighter color represents a smaller value. We'll see one in just a second. And then we've got a line graph. Goodness, everybody's seen a line graph, so we'll look at one real quick, but that's it. Hey, nothing too special about them. But let's look at one of these heat maps. So you'll probably recognize what they are when you see this one. Okay, so this one says we've got a map that shows the percentage of the population under 5 years old, and it's for each state. And it says, based on this map, if you wanted to start a children's clothing boutique, what area of the country might be the best option and why? So we're asking, what area of the country has the biggest population under 5 years old. So here's our heat map here. Okay. So the darkest color represents population having between 6.6 and 8.2% of the people under age 5. And then the lightest is 4.4 to 5.7%, and then we got values in between. So if you had a company that sold a lot of products to people that had small children, where would you want to have that company? Texas would be good, yeah. Oklahoma, somewhere in that area, right? It looks like we kind of have a line down the middle of the country that has a young population. Okay. And then get up here in the Northeast, we're down in Florida where a lot of people retire. You get more old people, young people. Okay. And we don't have a whole lot of in Alabama. Okay. When's that from? 2018 is when that's from. I want a date on there, right? Okay. All right, and then one line graph. Okay, we got the consumer price index, which is they take these particular goods. It's usually like a loaf of bread and a gallon of milk and things like that, and track how the price changes over time. What's going on here? Just increasing as time goes on, how much it costs to buy stuff. And that's inflation type of discussion. We're not an economics class, but that's what's going on there. Okay. Questions on any of those? Have you recognize this type of graph before? Have you seen one of these anywhere? Somebody? Especially since COVID. Okay, and see stuff like this all the time. And they've been using it a lot with their information campaigns here lately. So, and then you can get like the state map that gives county by county breakdown and all that kind of stuff. Okay, they are trending right now for sure. All right, so that's it for 2.2. One more to go, and it's more interesting and shorter. So if you can't get excited about that, man, you have a short section that's interesting. It's good stuff. Let's take a look at it. Okay. So 2.3, we're thinking about analyzing some graphs. All right, so we talked about 4 little things that make a graph a good graph. Okay, but we want to be a little more analytical than that. Okay, we had our, they got the same typo in here twice. We had our little slide that gave us that. We need the title, labels, source, and the date to make a good graph. I also need to think about other things that could go on and make a graph better or worse. Okay, we do have just a little bit of vocabulary here, and I don't think we even need this first slide of vocabulary, but we do have one more graph that sneaks in here. Okay. The pictograph. It's kind of funny because probably the first time you saw a pictograph was in kindergarten. And then you probably didn't see too many. But now, like if you look up health data from Johns Hopkins or somewhere, they'll have it in a pictograph. Okay, so I don't know. I guess our attitude, societal attitude, we kind of thought it was childish, and then now we're kind of back to it. So all it does is basically like a bar graph, but instead of having a bar that's a certain height, you have little pictures of something. Like with disease spread, they have pictures of little people, right? You have a little stick man on there instead of a bar, right? And you have more stick men if you have more people in that category and less if. Okay, so back to our thinking about analyzing a graph here. Okay. This next graph, we've got some data from about the federal minimum wage. Okay. This is unadjusted for inflation, so it's really not that meaningful to me if you don't adjust for inflation. So just keep that in mind when we're looking at the graph. Okay. But let's see if we can find anything that's maybe misleading with our graph. This graph's got an issue. It's not one of our four things. It's got a title, it's got labels, it's got a source, got a date. So it's not one of those four things, but we've got something else going on here that is a common problem. Sometimes it's done intentionally, but I think a lot of times it's done unintentionally. Okay. But you will see this issue come up if you look for it. I mean, this is data right from the federal government. Okay. But this graph's not got a problem with it. Anybody see anything? Mm-hmm. Yeah, if you're in the back, it's probably hard to see, but so the dates down here, we got October 24th, 1938, October 24th, 1939, October 24th, 1945, 25th of January, 1950, 1st of March, 1956. So what's the problem? These little tick marks down here, they're not to scale. Yeah, they're not even. Okay. And you will see that we would say this does not have a consistent scale on the x-axis. Okay. Yep.
Do people do that to like?
You could.
Linear or like.
You could definitely do that and hope nobody's paying attention. Right? You know, it's hard to say how often people do that maliciously, right? Actually trying to, but it does happen. It does happen. Sometimes it doesn't make that much of a difference. On this one, it doesn't really change too much about what you would get from the graph, but it's not a good habit. Okay? Not a good habit, because what happens to a graph, if you haven't think back to, I guess, algebra or maybe a little geometry with me here. If you can make the graph, if you change the scale on one of the axes, you can make the graph look like it's doing different things. Right? If we took and made the x-axis shorter with this same data, it would look like it was going almost straight up. Right? Or if we took our x-axis and we stretched it out, what would it make it look like? It'd make it look like it was almost flat. Right? So what's going on here, you can't trust how steep or how flat the little lines between each segment are, okay? Because they're not consistent. Okay? If we fix it, we've got the better graph here. If we fix it, this is what it should look like. Okay? And really, overall, on this particular one, not that big a deal, maybe. It is different, okay, but really the places where I notice it is at the end, it looks a little steeper, and then on the other one. But what should be done, right, is it should be spaced out. You should have a consistent axis down here. So here, the places that are labeled on the x-axis, they're all the 1st of January, and it's every 5 years. Okay, it doesn't change the data, but it just changes where your dot goes right on there. And you get a more accurate picture. Okay. Does that make sense why we want the scale to be reliable, we want it to be consistent? Okay. All right. So one more idea, and then we'll be done for today. Okay. How we're doing. One more idea here, and to me, this is the most important topic we cover in this chapter. Okay. It's not hard, but it's the most important topic that we cover in this chapter, and that's coming up with a way for us to talk about the shape of a data set or the shape of a distribution. Okay. We said a distribution was a way we talk about the structure of some data. So we talk about the shape of a distribution. Okay. So here we've got 4 basic categories, 4 basic shapes. And our goal is if we see a graph of some data, we want to be able to put it in one of these 4 categories, or say it's this shape or this shape or this shape or this shape. Okay. And before we can talk about those, we've got one more vocabulary term. One more vocabulary term that is popping up now, and it'll pop up over and over and over again. Is this idea of an outlier. Our definition here says an outlier is a data value that falls outside the normal shape of the graph. So if we're looking at a graph, if we've got some data value that doesn't look like it fits in with the rest of the picture, we call that an outlier. There's different ways to define that. All right, so let's look at our shapes. Okay, the first one, uniform, okay, would mean like if we're thinking about a bar graph or something here, we would call our shape uniform if the height, the y value, or the amount of data in each category is all about the same. Okay? It doesn't have to be perfectly exact, okay, but if it's pretty close, here all our bars are pretty close to being the same height. All these digits occur about the same number of times in Social Security numbers in the last 4 digits. Now we would expect that, right? We'd expect it to be pretty random. So that would mean that they all occur about the same number of times as each other. It would be weird, and we would start looking for a reason if, like, we noticed everybody had a 7 in the last digit of their Social Security number, just about. So we wouldn't expect that, right? We expect them to be pretty even. So here we would say the shape of this graph, the shape of this data is uniform. Okay. The second one is symmetric or symmetrical. You'll hear it called both things. Okay, so they both mean the same thing. I don't know if they're just interchangeable or what's going on there, but our textbook uses both. I say both. Everybody I've heard uses a mix. Okay, so maybe they're just two ways of saying the same thing here. Okay, the idea here is if we think about the middle of our graph or the middle of our data, if we think about drawing like an imaginary line somewhere down about the middle of our data, then they should look like reflections of each other, or close. It doesn't have to be exact. So like here, we're saying the left side of this data set, if we flipped it over to the other side, it would kind of match up. Right? They're symmetric. It's our normal idea of symmetry, if you're familiar with that. Or you could think about like if we folded it down the middle, the bars would kind of overlap each other. Right? So look like mirror images of each other. And again, it doesn't have to be exact, right? Like this bar would be a little bit higher than this one, but it's pretty close. Very close. So that's symmetric or symmetrical. This is not the only way we can have symmetry. Right? It's not the only way it can be symmetric. What else could we have? We could have data that look like this, right? These are our bars. Then if we drew a line down the middle, then it would still be like mirror images, right? Even though it's not like a hill, like here it'd be like a valley. Okay. Or what else? What about our last one? What if they're all the same height? If we draw one, think about that. Then here our left side looks like a mirror image of our right side. So really a uniform distribution is just a special case of a symmetric distribution, a symmetric shape. Okay, so it's one type, but a special type of symmetrical. Okay. And then everything else we just call symmetric. We don't have a special name for all the other ones. Okay. Two more. Oh. And these two are, we've got skewed to the left, skewed to the right. It's the same idea, just one's on one side, one's on the other. Okay, but that part's a little tricky. Okay, so you need to get in your head which one's which, because it's easy to, when you're first learning especially, to get it mixed up. I'll tell you how I remember. Let's look at skewed to the right. It's the first one we have. So what's happening here is that most of our data is over here on the left side of our graph. But over here on the right side, we've got this like one or two little data values that's kind of off by itself. You remember what we call that? Outlier. Okay. So if you think about trying to turn this into a curve, like instead of bars, right? What we would say is we've got like the right side stretched out skinny. Okay. Most of our stuff's over on the left side, got a skinny little tail. What we call that? Little tail over on the right side. So that's skewed to the right. So the side where the skinny tail is, the side where the outliers are, is skewed that way, skewed to the right. And we can have the opposite situation. Okay. We could have some data where most of our data was on the right side, but we've got an outlier or two over on the left side. So that kind of stretches out that side of our graph. So that would be skewed to the left. Okay. So the skinny tail, that's what I keep track of. If the skinny tail's on the right, it's skewed to the right. Skinny tail's on the left, it's skewed to the left. And then it's also good to remember the skinny tail's on the side where the outlier is. Or outliers, you could have more than one. Okay. Questions there? All right, I got one for us to practice. We'll be done. So there's all that stuff we just said. Okay. It's in there and it's posted on Canvas if you want to get all that. Okay. Here's the distribution. What shape would we call this? So if we ask what shape a data set is, we've got four possibilities. Right? Okay, I've got some symmetric. I got other thoughts? Maybe? Thinking? Okay, so this one, okay, it's not uniform because all the bars are not about the same height, right? The question is, would you call this one symmetric or would you call it skewed one way or the other? Okay. But we can say for sure, no matter how it looks, for sure that this one is symmetric. Okay, because if we draw a line down the middle of our data, this one's just about perfect. And just we have a nice little curve there if we think about that. The temptation, because of this gap over here, is to say maybe it's skewed to the left. Okay, so here's my word of caution there. It can't be skewed to the left because what's not over here? We don't have an outlier over here. There's no data over here. Okay? So this whole thing is like shifted over to the right, like it's slid over to the right, but it's not skewed because we don't have any data over there to stretch out the tail on the graph. So just be careful of that. That's kind of confusing a little bit sometimes when you're starting to think about these. Okay. Questions? All right, well, that's it. I will see you next week. Okay. These assignments are due next Thursday, so you got to file on these. Get started on them as soon as you want to. You're ready. If you did not sign the sign-in sheet, where'd the sign-in sheet make it to? Okay, thank you. If you did not sign the sign-in sheet, I'll put it on the table over here by the door, and you can get on there as you leave. Which hall?
Angle Hall?
Oh, it's Angel. I know it's spelled like Angle. It's the one that's right across like the little road here in Ayers.
Okay.
Yeah. Do, 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 do.